In the ever-evolving landscape of cyber threats, SQL injection stands as a persistent and potent weapon in the arsenal of hackers. This technique, often abbreviated as SQLI, preys on vulnerabilities in the way websites and applications interact with databases. By exploiting flaws in input validation, attackers can manipulate SQL queries, gaining unauthorized access to sensitive information. Imagine a scenario where a malicious actor gains entry to a treasure trove of customer data, including credit card numbers and social security numbers. The repercussions of such breaches can be devastating, resulting in financial losses and reputational damage. SQL injection attacks have been plaguing the digital realm for over 2 decades. This guide delves into the intricacies of SQL injection, providing a clear explanation of how it works, its potential consequences, and steps to prevent it. Before we delve into the technicalities of SQL injection, it's crucial to grasp the fundamental concepts of databases and how they interact with web applications. Databases are the backbone of modern web services, storing everything from user information to transaction records. At its core, a database serves as an organized repository of information, meticulously structured into tables with rows and columns. Each table is designed to hold specific types of data, making it easier to manage and retrieve information efficiently. Web applications act as intermediaries between users and databases. They provide a user-friendly interface for interacting with the data stored in these databases. When you interact with a website or an app, the application sends requests to the database to retrieve or modify the relevant information. This seamless interaction is what makes dynamic content possible. These requests are formulated in a specialized language known as Structured Query Language, or SQL for short. SQL is the standard language for managing and manipulating databases. SQL commands are the instructions that web applications use to communicate with databases. They are essential for performing various operations on the data. They allow developers to perform a wide range of operations, such as retrieving specific data, inserting new records, updating existing ones, or deleting information from the database. These operations are fundamental to maintaining the integrity and usability of the data. For instance, a simple SQL query to retrieve a user's profile information might look like this. Select asterisk from users where user_ID =1. Understanding this interplay between web applications, SQL queries, and databases is essential to comprehending how SQL injection attacks exploit vulnerabilities in this communication channel. By grasping these basics, you'll be better equipped to understand the complexities of SQL injection and how to defend against it. The crux of SQL injection lies in the exploitation of a security vulnerability known as improper input validation. This vulnerability allows attackers to manipulate the queries that an application sends to its database. Web applications collect data from users, such as usernames, passwords, search queries, or form submissions. These inputs are often used to build SQL queries that interact with the database. This data is then used to construct SQL queries that interact with the database. However, if the application does not properly sanitize or validate the user-supplied input, it can lead to serious security issues. If the application fails to sanitize or validate the user-supplied input effectively, it creates an opening for attackers to inject malicious SQL code. This can compromise the integrity and security of the database. Essentially, they trick the application into treating their malicious input as legitimate SQL commands. This allows them to execute unauthorized actions on the database. Let's illustrate this with a simplified example. Imagine a login form that asks for a username and password. Consider a login form that asks for a username and password. The user enters their credentials and the application constructs an SQL query to verify them. A typical SQL query used to authenticate a user might look like this. Select asterisk from users where username =user and password =pass. If the application fails to sanitize these inputs, an attacker could enter the following string in the username field: admin or 1 =1. The manipulated query now becomes select asterisk from users where username =admin or 1 =1 and password =pass. This query always returns true, allowing the attacker to bypass authentication and gain unauthorized access to the system. To further solidify our understanding of how SQL injection works, let's compare a legitimate SQL query with a malicious one. Imagine a website with a search functionality that allows users to search for products based on keywords. A typical SQL query for this functionality might look like this. For example, if a user searches for laptop, the query would return all products with laptop in their names. Instead of entering a simple keyword, the attacker could enter the following string in the search bar. When this malicious input is incorporated into the SQL query, the resulting query becomes the command is used to delete an entire table from the database. Section 5. Real-world ramifications when SQL injection strikes. The consequences of successful SQL injection attacks can be far-reaching and devastating. These attacks can compromise sensitive data, disrupt services, and cause significant financial and reputational damage to organizations. Let's examine some real-world examples of SQL injection attacks. Data breaches. In 2011, Sony PlayStation Network suffered a massive data breach attributed to an SQL injection vulnerability. This breach exposed the personal information of millions of users. Hackers gained access to the personal information of millions of users, including names, addresses, email addresses, and credit card details. The aftermath was chaotic, with users scrambling to secure their accounts and monitor their financial statements. The breach resulted in significant financial losses for Sony and eroded trust among its users. The company faced lawsuits and had to invest heavily in improving its security measures. Financial theft. In 2017, a group of hackers exploited an SQL injection vulnerability in a payment processing company, gaining access to millions of credit card numbers. This breach highlighted the vulnerabilities in financial systems. They then used this stolen financial information to make fraudulent purchases, causing widespread financial distress for the affected individuals. Website defacement. Hacktivists often target websites with SQL injection attacks to deface them and spread their message. These defacements can damage the credibility of the targeted organizations and spread misinformation to the public. Section 6. The many faces of SQL injection beyond the basics. While the basic principle of SQL injection remains the same, exploiting improper input validation to manipulate SQL queries, the techniques employed by attackers are constantly evolving. Here are some common types of SQL injection attacks. The attacker injects malicious SQL code directly into the vulnerable application's input fields. The attacker doesn't see the direct results of their injected queries. This type exploits the database server's ability to make connections to external systems. The malicious code is not immediately executed but is stored in the database. Attackers can exploit vulnerabilities in stored procedures to execute malicious code with elevated privileges. Understanding the different types of SQL injection attacks is crucial for security professionals. This knowledge helps in effectively assessing vulnerabilities and implementing appropriate countermeasures. Section 7. Shielding your data. Prevention is key. Preventing SQL injection attacks requires a multifaceted approach. Here are some essential tips to safeguard your databases. Validate and sanitize all user-supplied input before processing it. Parameterized queries treat user input as separate parameters, preventing malicious code injection. Grant database users and applications only the necessary privileges. Conduct regular security assessments and penetration testing. UAFs filter out malicious traffic and block SQL injection attempts. DAM solutions provide visibility into database activity. Keep your software up to date with the latest security patches and updates. By implementing these preventive measures, organizations can significantly reduce their attack surface. Section 8. Staying ahead of the curve, the evolving threat. The threat landscape is constantly evolving, and SQL injection is no exception. Attackers are constantly devising new techniques and bypassing existing security measures. Here are some emerging trends in SQL injection attacks. The availability of automated SQL injection tools has lowered the barrier to entry for attackers. Attackers are increasingly targeting business logic flaws in applications. Attackers are now setting their sights on NoSQL databases, such as MongoDB and Cassandra. Attackers are beginning to leverage machine learning to automate the process of discovering and exploiting SQL injection vulnerabilities. To stay ahead of these evolving threats, it is essential to adopt a proactive and adaptive security posture. Section 9 Conclusion: A call to action for database security. SQL injection remains a significant threat to the security of web applications and databases. By understanding the mechanics of SQL injection and implementing prevention techniques, organizations can mitigate their risk. Implementing secure coding practices, robust security measures, and continuous monitoring is crucial. By prioritizing database security, we can collectively create a more secure and resilient digital world.